Alright, welcome back. This is lesson 20 of our semester-long series of videos on basic circuit analysis. Lesson 20 is average power and maximum average power transfer. So something has been suspiciously omitted from our calculations since we've been dealing with AC circuits. And yep, that is power. Right? We've been investigating the voltages and the currents across capacitors, inductors, and resistors, but we've never mentioned at all, actually, the power being absorbed and sometimes supplied. Remember, the inductors and the capacitors can store energy, so they can actually temporarily supply power as well. Alright, well, let's start with instantaneous power. And let's assume that I have some circuit element, or we'll call it a passive linear circuit or network. So this is fancy for saying contained in this box are resistors, capacitors, and inductors. That's a passive linear network. Yes, the capacitor and the inductor can supply power, but they have to be charged first. They have to be given power, and they store it, and then they can supply it. So they are passive elements. And resistors, of course, absorb power. And let's say we have some source over here. And I'm going to leave off the details because I don't want to assume it's voltage or current, so I'll just put a source. And we're going to connect it to our network. And so across our network will be a voltage V of T. Right? And since it's passive, we'll make the current arrow go from positive to negative. So the current is going this way. Call that I of T. Now, in DC circuits, we said the power is I times V. And this is the definition of electric power. You need some I, you need some V. And power is I times V, and this has units of watts. Alright, well, it won't surprise you then in AC, so this is at DC, that this must be true then at every slice of time now. These V and I are changing with time, so every slice of time this holds, right? So now we have, for AC circuits, the power, P of T, it's a function of time, is I of T times V of T. Okay, so you give me an instant in time. Okay, say T equals 1 second, and I'll ask, well, what is the current? So I'll plug in 1 second for I, and if you know the current, then you can tell me what I is. And I'll plug in 1 second for V, and then multiply those two, and that's the power at 1 second. That's straightforward. That's called instantaneous power. Okay, I'll write it again. Instantaneous power. Now, let's, in the general case, say that V of T is a sinusoid, so it has some maximum value, Vm, and we'll just write, say, a cosine, although I could have chosen a sine or a complex exponential, and it has some frequency omega. We'll say it has some phase, and we'll call it theta V. Right, and let's say the current also is going to be a sinusoid, and it will have an amplitude Im. We'll say it's a cosine wave. Now, as you should have already seen and understood, a linear system or a linear network does not change the frequency. So this has to be omega. So these are going to be the same frequencies, definitely. But the amplitudes will be different, and the phases will be different as well. So we'll call this theta I. Alright, so our instantaneous power then, if I plug these guys in, Vm, Im, cosine omega t plus theta v times the cosine of omega t plus theta I. Now, there is a trig identity that I'll write in green to remind you. Okay, it says that the cosine of A times the cosine of B is 1/2 times the cosine of the difference of those angles, A minus B, plus the cosine of the sum of those two angles. So this is a beautiful identity. It says you have cosine of A times the cosine of B. It's the average of the cosine of the difference with the cosine of the sum. It's pretty cool. So if I make use of that identity over here, right, where I have to call this thing A, omega t plus theta v, and this thing B, omega t plus theta I, then I get the instantaneous power is Vm Im times 1/2, so I'll put this over 2, cosine of this thing, omega t plus theta v minus this thing, so the omega t's drop out. So this is theta v minus theta I plus then omega t plus theta v plus omega t plus theta I. So this becomes cosine of twice omega t plus theta v plus theta I. Alright, well that's of interest to us, and let me distribute the 1/2 and the Vm and the Im in. So I've got 1/2 Vm Im times cosine of theta v minus theta I plus 1/2 Vm Im times the cosine of 2 times omega t plus theta v plus theta I. And this is in watts. Just put the W in watts. Now this is interesting because there are two pieces to this. And the first piece here, you'll notice, is independent of time. So it's not oscillating at all. It's not a sinusoid. It's a constant, right? And it's a constant that depends on, of course, the amplitudes of voltage and current, but also the difference in their angles. But it does not change with time, so that's a constant. Then we have this piece, and of course this is a sinusoid. Okay, so it does change with time, but notice its frequency is twice the frequency of our voltage and current. Sinusoid of twice the frequency of V and I. Alright, so I'm going to make a sketch of this. P of t. Right, so first of all, there's that constant term that's independent of time. So this is positive, or let's say it could be positive. So I have to draw something here. So I'm just going to make an assumption that maybe that constant is up here. And then this thing is going to oscillate with time. So what we have is something like this. Where this value, the middle of that wave, right, is this, or what we'll say, the distance from there to there, that's 1/2 Vm Im cosine of theta v minus theta I. So that's that constant term. So the sinusoid is shifted up by that much, that constant. And then from there, from that midpoint, the amplitude of this sine wave is this thing, 1/2 Vm Im. 1/2 Vm Im. And this thing goes down by that much as well, 1/2 Vm Im. So what this tells us, and we'll even put the period in here. So remember, if the period of, or if the frequency of our voltage and current was omega, so I'll write this in blue at top right here. Omega is 2 pi over t, right? So if this sinusoid has twice the frequency, then this thing's period is half t, right? If you double the frequency, then you half the period. So where does this thing repeat? That's about right here. So this is t over 2 is where it starts to repeat. Now you'll notice that in general, in the general case, the sinusoid is positive, so the instantaneous power is positive, okay, but sometimes it's also negative. Okay, so in general it's positive and negative. When it's positive, that means the current is flowing from source to the passive linear network. Okay, that means the network is absorbing power, right? We chose these directions and these polarities. Current flows from positive to negative, so that's positive power. So again, the network is absorbing power when the power is positive. But the power can dip negatively, so that means the current is going the opposite way, and the source is absorbing the power. This is possible because, again, the capacitor and the inductor can temporarily store energy. So, on the positive part of the cycle, current is flowing in, and the capacitor and the inductor are storing energy. Then, for the negative part of the cycle, that energy is being released the other way, and the source is absorbing energy. Good. Now, if we wanted the average value, this is what we're trying to get at, it's the average value of the power. You see, because the power really, the instantaneous power is not that useful to us. Imagine this thing, the frequency is 1,000 radians per second. Okay, so it's going up and down very quickly. Why would you want to know what the power is at exactly 0.01 seconds or something like that? Okay, it's really not that useful to us to know the power at an exact instant of time. What usually we're concerned with is the average power. Tell me on average how much power the passive linear network is absorbing or supplying and so forth. Actually, it can't on average supply any power because it's passive. So tell me on average, how much is this thing absorbing? Okay, why this is important is because this has implications for example, battery life in phones and computers and so forth. The battery life is going to be related to the average power that its components absorb. All right, so now mathematically, if I want the average power of this thing, the average value, so we'll represent that as a bar over the p, excuse me. Mathematically, we can use the average value theorem, or the mean value theorem, I guess. And so if I want the average value of something that repeats, right, all I need to do really is take the average value of a period, right? So if this thing is periodic, just tell me the average value over one period, and then that repeats. So the period of the power was t over 2. So all I have to do is integrate over some, we're gonna take this notation to mean some t over 2, some window that's t over 2 in length, right? And then divide by t over 2. I'll assume that you've had the mean value theorem by this point, and then we're going to integrate the power dt. This gives us our average power. Okay, I'm going to clean this up a little bit. Make some room. All right, well, if I substitute this thing, right, this was our power, into the integral, and I don't want to write this out again, so I'll just say what we have is the integral of this thing is a constant. This thing is a constant, so when I integrate it, right, I get 1/2 Vm Im cosine of theta v minus theta I times t over 2. And because of the 1 over t over 2, I'm dividing over here by 1 over t over 2. This is what I get when I do the integration. I just tack on the width of the time because it's a constant. So the t over 2's cancel, and the integral of this thing is simply the thing back. Okay, the integral of the first term is simply the first term. That makes perfect sense. The average value of a constant is simply that constant. Now what about the average value of this thing? Well, the average value of this thing, we're integrating over a half period. Half a period of the original voltage and current waveforms. But this is twice the frequency. So we're integrating over one period of this thing. Well, when you integrate a cosine over one period, what do you get? You get 0, right? So the average value of this thing, p bar of t, is just this constant here. That's very nice. Okay. This is the average power. Now, if you want the instantaneous power, you have to be in the time domain. You have to use, of course, if you want the instantaneous power at some time, right, you have to know the voltage at that time and the current at that time. However, average power, you see there is no t here. So we can express the average power in the frequency domain. Okay, let's first note, let's make an aside in green over here. notice I've erased it. We had V. We were saying that V was Vm cosine of omega t plus theta v, and we were saying that I of t was Im cosine of omega t plus theta I. Okay, now consider this multiplication, 1/2 v times I complex conjugate. Let's see what we get from that. Well, this is 1/2 times Vm, right? So V, the voltage, has an amplitude Vm and a phase theta v. So we'll say this is theta v, right, expressed in polar form, and I is Im with an angle theta I, and that's I expressed in polar form, and so we're going to take its complex conjugate. So this is 1/2 Vm times theta v, excuse me. When you take the complex conjugate in polar form, remember that's a reflection over the real axis, so we negate the angle. So this becomes Im negative theta I, and when we do that multiplication, we have 1/2 Vm Im, the amplitudes multiply, and the angles add, so we've got theta v minus theta I. Okay? And hang in there. This is 1/2 Vm Im. If I write it in exponential form, j times theta v minus theta I. And from Euler's theorem, this is 1/2 Vm Im cosine of theta v minus theta I plus j sine of theta v minus theta I. Remember Euler's theorem, or Euler's equation, was that e to the j theta is cosine theta plus j sine theta. Alright, now let's compare this result to this, our average power. Okay, and you see the first term, the real part of this thing. Okay, here's the real part, because there's no j here. This is the imaginary part. So we can, the real part is the average power. See that? Make that comparison there. So we conclude that the average power is 1/2 times the real part of V times I complex conjugate. And again, that's equal to this thing in the box too. So this is kind of in time, if you like to call that, even though the time is not there. This is in phasor form. Alright, I'm going to erase the aside down here in green. Erase this. Now, two important special cases I wanted to consider. Okay, the first is when theta v equals theta I. So remember, theta v is the phase of the voltage, theta I is the phase of the current. So we're saying when they're in phase with one another. the voltage and the current are in phase with one another for resistive loads. So a few videos ago we plotted the voltage and the current across and through a resistor, and we showed that they were in phase with one another. So this is the case of a resistive load. In this case, the average power absorbed by a resistive load is 1/2 Vm Im cosine of 0, which is 1. And recall that, of course, the magnitude of the voltage is the magnitude of the current times the resistor. So if I plug that in here, I get the average power absorbed by a resistor is 1/2 Im squared times R. And the magnitude we've been writing in phasor form like this. We've just been calling that I, actually. Okay, the amplitude is can be written like with the absolute values. Right, so this is the average power in a resistive load. This is always positive. So that means, again, resistive loads never supply power. Never supply average power. Okay, the next case I want to consider is when the angles are different by 90 degrees. Now, the cosine is an even function, so it does not matter if the voltage lags the current by 90 degrees or if the voltage leads the current by 90 degrees. The cosine of the difference will be the same. Okay, so when does the voltage lead the current by 90 degrees, and when does the voltage lag the current by 90 degrees? Well, that's the capacitive and inductive loads, right? A few videos ago we plotted the capacitor's voltage-current relationship, and we saw that the voltage lags by 90 degrees. We did the same thing for the inductor, saw that the current lags by 90 degrees. So for either one of those two, the difference in the phases is 90 degrees. And again, it doesn't matter if it's negative 90 or positive 90, the cosine of either one is going to be the same. And so what is the cosine of 90 degrees? It's 0, right? So in this case, the average power is 0. So this is because the capacitor receives power, right? It absorbs, and then it supplies power. Absorbs, then supplies. Absorbs and supplies. Same with the inductor. And so on average, neither one is supplying or absorbing power. Okay, let's look at a couple examples now. Okay, given that V of t equals 120 cosine 377t plus 45 degrees volts, and I of t equals 10 cosine 377t, same frequency, right? Has to be, minus 10 degrees amps. Find the instantaneous power and the average power absorbed by the following circuit. Let's call it, I guess we call it a network. Okay, so we had this thing, remember? Here was our passive linear network, and this was V, and this was I. Okay, so we'll find the instantaneous power, that's P of t, equals V times I. Right, so V of t times I of t. So that's 120 times 10 is 1200. Then we have cosine of 377t plus 45 degrees. And then times cosine of 377t minus 10 degrees. Watts. And from that trigonometric identity, right, cosine of A times the cosine of B is the average of the cosine of the sum with the cosine of the difference, we can reduce this to P of t equals 600 times the cosine of twice the frequency, 754 t plus 35 degrees, right? So there's the addition of the two angles, plus the cosine of twice the frequency, excuse me, the constant term drops out. So this is gone. Cosine of 55 degrees. Okay, so let's clear this up a little bit. So I'll write it out again, the trig identity. The trig identity I'm using here, if we call A to be 377t plus 45 and B to be 377t minus 10, I'm using cosine of A times the cosine of B is 1/2 cosine of A plus B plus cosine of A minus B. So A plus B, right? A plus B gives me twice the frequency and an angle of 35 degrees. That's this thing. A minus B, the time cancels, and I'm left with 55 degrees. And then the 1200 becomes 600 because of this 1/2. Right. Now, this is watts, and cosine of 55 is just a constant, right? So you can factor the 600 through, multiply by that constant, and you're left with 344.2 plus 600 cosine of 754t plus 35 degrees. Remember when we said that the instantaneous power had this constant plus a sinusoid at twice the frequency? There it is. That's the instantaneous power. You tell me what time it is, t, and I'll tell you what the power is, p of t. Now the average power, p bar, we said was 1/2 Vm Im cosine of the difference in those two phases. That was one way we wrote it. This was the time way we wrote it, and we wrote it again in frequency domain. All right, so this is 1/2 the amplitude of the voltage, that's 120, times the amplitude of the current. So this also gives us 600 when we do the 1/2 of that, times the cosine of the differences in angles. So the difference in angle is 55 degrees. Okay, that's exactly this calculation. Do that on your calculator and you'll get 344.2 watts. And again, I just want to call attention to it that that's this number here. The instantaneous power is that average power plus the sinusoid. And here's the average power. Alright, let's do one more example. And we're going to move on to maximum average power transfer. Okay. Yeah, let's do one more. Okay. Calculate the average power absorbed by impedance Z equals 30 minus J70 ohms when voltage V equals 120 angle 0 degrees is applied across it. Okay? So we've got a voltage and a current. A voltage and an impedance. We can get the current. The current, according to Ohm's law, is 120 angle 0 degrees, okay, divided by 30 minus J70 ohms. Right, so we can convert the denominator to polar if we like. 76.16 angle negative 66.8 degrees ohms, and do the division, and we get the current as 1.576 angle 66.8 degrees amps. Okay, so there's the current going through this impedance. So the average power, P of t, okay, is 1/2 Vm Im times the cosine of the angles between. Right, so this is 1/2 times the magnitude of the voltage, that's 120, times the magnitude of the current, that's 1.576, times the cosine of the angles in between them, cosine of 0, right, minus 66.8 degrees, watts. So this gives us 37.24 watts. This thing is absorbing on average. Alright, so we just saw that the average power absorbed by some component is 1/2 times the real part of V, the voltage across that component, times the complex conjugate of the current through that component. That's also equal to 1/2 times the amplitude of the voltage times the current amplitude times the cosine of the angle in between the voltage and current waveforms. All right. Now I write P of t here. P of t was the instantaneous power. Okay, and the bar means average, the average of the instantaneous. So the average power is not a function of time. There's no t here. Okay, because of the bar, it's time averaged. But here is our average power. Now we're going to move to maximum average power transfer. So let me just remind you in DC, okay, when we acquired the Thevenin equivalent circuit of a DC circuit, we found that the resistor that we wanted to connect to the circuit ended up being equal to the Thevenin resistance. So this had to be true, right? We match the Thevenin resistance to our load resistor, and that's the load resistor we would connect to draw as much power as possible, or to absorb as much power as possible from the circuit. So we're going to do the same thing with AC circuits, and whatever result we end up with, if we move to the specific case where the Thevenin impedance is purely real, then it has to reduce down to this. So that's a way of checking our result. It has to reduce down to this if the Thevenin impedance is purely real. Also, just to remind you that the maximum power that we got was V Thevenin squared over 4 times the Thevenin resistance. This is the maximum amount of power that a circuit can draw, or supply, excuse me, that a circuit can supply, or that equivalently that a load resistor can draw from the circuit. Alright, so we're just going to do the same thing with AC circuits. So in the last video, you found a way of finding the Thevenin voltage of an AC circuit and a Thevenin impedance. And we're going to write that Thevenin impedance in terms of its real part, call that R Thevenin, and its imaginary part, call that X Thevenin. Okay, so we're writing it in rectangular form. The question now is, what impedance should I connect to the circuit, call that ZL, load impedance, in order to absorb the maximum amount of average power? And how much is the most, or the maximum average power that I can get from this circuit? So we're going to call the load impedance RL plus J times XL. So the question is, what is RL and what is XL in relation to these guys over here? And how much power can I get? Alright, well, the current going around that loop is the same as the current through the load, call that IL. So we can use Ohm's law. IL is V Thevenin divided by the sum of these two impedances. So I have them in rectangular form already, so the real parts add and their imaginary parts add. There's the current, load current. Also, well, actually before we get to that, I'm going to use this equation here for the average power. Okay, and so I need I's complex conjugate. So let me do that. Take the complex conjugate of this thing. Now, that's when you turn the J's to minus J's. But also remember that V Thevenin itself is a phasor. It has a magnitude and an angle or equivalently as it has a real part and an imaginary part. So we'll write the complex conjugate of this thing is V Thevenin complex conjugate over R Thevenin plus RL, that's the real part, minus J X Thevenin plus XL. Alright, now back to the voltage. The voltage across that thing, call that VL. This is a series circuit, so I can get VL with voltage division. This is V Thevenin times the impedance whose voltage I want, RL plus JXL, over the sum of these two impedances. That's, again, this thing here, this denominator. We can group the real parts together, and we can group the imaginary parts together. Like that. Now then, the average power is 1/2 times the real part of this expression times this expression. So let me write that down. 1/2 times the real part of, now I'm going to call this equation 1, call this equation 2. I'm going to multiply equation 1 with equation 2. So first of all, you'll notice I have V Thevenin times the complex conjugate of V Thevenin. So when I take a complex number times its complex conjugate, I get the magnitude squared. So this becomes the magnitude of V Thevenin squared times RL plus JXL over. Alright, now notice the denominators here when I multiply 1 and 2. I've got the complex conjugate, so this we've been doing a lot. I encourage you to factor or distribute, FOIL this thing out, but what you get is the magnitude squared. You get R Thevenin plus RL squared plus X Thevenin plus XL squared. Alright, moving right along. I need 1/2, I need the real part, 1/2 times the real part of this. Well, the magnitude of V Thevenin, magnitudes are real, so I'll keep that guy. And the denominator is real, so the only thing that we're going to lose here is this JXL, that's part's imaginary. So now I've got the magnitude of V Thevenin squared times RL over R Thevenin plus RL squared plus X Thevenin plus XL squared. Alright, so I'm going to label this as equation 3 so I can reference it. And equation 3 is what I want to maximize. So now we're going to say that our load resistor is, or our load impedance is variable. Okay, so I can change RL and XL at will, and I want to know what's the RL and what's the XL to maximize equation 3. So let's start with the partial derivative of P bar with XL. Okay, so I've got some constants here. I'll just write those constants down. Times the derivative of 1 over this denominator. So that's the bottom times the derivative of the top. The derivative of 1 is 0. Minus the top 1 times the derivative of the bottom. Derivative of the bottom is 2 times X Thevenin plus XL. All over the bottom squared. The bottom squared doesn't really matter because in the end I'm going to set this thing equal to 0. So what I need is the numerator to be 0, right? The numerator divided by some non-zero, 0 divided by some non-zero number is going to give me 0. So I'm just going to write the bottom squared down here. So let me solve this equation. I can multiply by the or excuse me, divide by the constants, but what I need is this thing to be 0. So that tells me that x Thevenin equals minus xl, or the imaginary part of the load impedance is going to be minus the imaginary part of the Thevenin impedance. That's the first half of our big result. All right, now let me take the partial derivative of equation 3 versus, with respect to the load resistor, RL. So I've got the constants, 1/2 the magnitude of the Thevenin voltage squared. Now I've got the bottom times the derivative of the top. Derivative of the top is 1. So let me just write the bottom. Okay. Then, so that's bottom times the derivative of the top, then minus the top times the derivative of the bottom. So the bottom, the 2 comes down in front, and I've got R Thevenin plus RL. And again, all over the bottom squared. I'm going to set that equal to 0. So I can divide by the constants if I like, but I need this thing in the big brackets to be 0. So notice here from our result from the previous derivative, xl equals minus x Thevenin. So this term's going to drop out. So in the big brackets, let me FOIL this out. I've got R Thevenin squared plus 2RL R Thevenin plus RL squared. And then if I distribute this in, I've got minus 2 RL R Thevenin minus 2 RL squared. That's got to be equal to 0. So now you see the 2 RL R Thevenins cancel, and I'm left with R Thevenin squared and minus RL squared. That has to be 0. And so the other half of our big result here is that R Thevenin equals RL. Whew. All right, so let's summarize that. Which load impedance am I going to choose? I'm going to choose R Thev minus J X Thev. That is, pick the load impedance. Pick the load impedance to equal the complex conjugate of the Thevenin impedance for max average power transfer. What a beautiful result. Now, remember what we said, that this has to reduce down to our DC result if the Thevenin impedance was purely real. So if the Thevenin impedance is real, then it can be written like this, R Thev. So what's the complex conjugate of a real number? Well, in this case, it's the same, right? So if the Thevenin impedance is purely real, then our load impedance is to match the Thevenin impedance, and that is the result that we had prior. But that's a general case. All right, so the last part of this then is how much power do I get? What is the maximum average power that I can get from the circuit? So this is equation 3 tells us the average power for any combination of XL, RL. So let's plug in this load impedance into equation 3 and see what we get as the maximum. One-half the magnitude of the Thevenin voltage squared. Now the load resistance that we're going to choose is equal to the Thevenin resistance. Okay, so here in the denominator I've got R Thev plus and then another R Thev. And here the x's, we're going to choose XL to be minus X Thev. So this is 0. So the maximum amount of power that I can get on average is the magnitude of the Thevenin voltage squared divided by 8 times the Thevenin resistance. What a wonderful result. Now we'll look at an example, one example, but I also want to point out to you again that it's slightly out of the reach of this course to find the Thevenin equivalent circuit of an AC circuit with dependent sources. So you will never be asked in this course to find the maximum average power transfer of an AC circuit with dependent sources. So let's look at an example with only independent sources. Find ZL to absorb the maximum average power what is that max average power? Okay, so let's write a circuit here. Let's say that this is 10 angle 0 degrees volts. And we've got 4 ohms, 8 ohms, minus J6 ohms, J5 ohms, and here is our load, ZL. Alright, so the first thing we need to do is find the Thevenin equivalent circuit. So let's find the Thevenin impedance. So we're going to remove the load, and we're going to short the voltage source. In this case, the Thevenin impedance is 4 ohms in parallel with 8 minus J6 ohms. And then all of that is in series with J5 ohms. So if I do the parallel combination, that's the product over the sum. So that's 32 minus J24 divided by 12 minus J6 ohms plus J5 ohms. And to help simplify this, let's take 32 minus J24 over 12 minus J6, multiply by its complex conjugate of the denominator, 12 plus J6 over 12 plus J6 ohms plus J5 ohms. Right? And when I do that, I get 2.93 plus J 4.47 ohms. So this is the Thevenin impedance. So find ZL to absorb the maximum average power. So from the result that we just got, I'm going to choose the load impedance to be the complex conjugate of this. This is my load impedance that I will choose to absorb the maximum amount of average power. Alright, now let's continue. I'm going to keep that load impedance removed, okay, but I'm going to bring back the voltage source. This was 10 angle 0 degrees volts. I'm going to find the open circuit voltage, and that is the Thevenin voltage. So because this is open, there's no drop across the J5 ohm impedance. So finding V Thevenin here, that the open circuit, that's equivalent to finding the voltage drop here. No drop across here. So I can get this drop across the series combination using voltage division. So V Thevenin is 10 angle 0 degrees volts times 8 minus J6 over 8 minus J6 plus 4, 12 minus J6. And this is volts. Okay, so again, if you like, you can multiply by the complex conjugate of the denominator over itself. 12 plus J6 over 12 plus J6. And I get V Thevenin is 7.45 angle negative 10.3 degrees volts. So what is the maximum amount of power? Average power? That was the, again, I'll write it down here, the magnitude of the Thevenin voltage squared divided by 8 times the Thevenin resistance. So what is the magnitude of this thing, this complex number? 7.45, right? So this is 7.45 squared, volts squared, divided by 8 times the Thevenin resistance, that was 2.93, and this is in watts. So this comes out to be 2.37 watts. That's the answer.